Okay, chapter 5, hydraulic pumps. There are many different kinds of hydraulic pumps out there. Objectives for chapter 5, hydraulic pumps, and describe the basic steps for creating fluid flow that are common to all hydraulic pumps. Isn't that the very definition of a pump?
Yep.
Kind of what I thought. Describe how hydraulic pumps are rated and distinguish the different ratings, mostly by the amount of flow that they can produce, capable of, and their pressure. Distinguish between the different types of hydraulic pumps that are used in hydraulic systems. Got gear pumps, piston pumps. I have seen a couple of vane pumps, but they're not very high pressure. They're just really high flow. Describe the specific actions that the different types of hydraulic pumps use to create fluid flow and pressure. The one that I always had the problem with understanding when I first started doing this stuff was the gear pump, because the way it works is counterintuitive to me anyway. It looks like it works backwards. Describe the different types of variable pump controls. You have variable flow and variable pressure. Those are the two types of variables. Identify safety practices used during pump repair, installation, and operation. Some of the pumps have very powerful springs inside of them. It's a big deal whenever you're taking it apart, because that spring can come out of there with enough force to take an eye out. Saw a guy that had part of his ear missing because a spring came out and just missed his eye when it hit his ear. And like when Trump got shot, it looked like that. Hydraulic pump is a mechanical device that changes mechanical energy into hydraulic energy. Fluid flow. Actually takes electrical energy, converts that into mechanical energy, and then that converts it into hydraulic energy. That's why the motor is called the prime mover, because if it doesn't work, nothing else does. Main categories of pumps are as follows: positive displacement and non-positive displacement. Pretty easy, yeah? Positive displacement. There's a vane pump. Pump rotates. In this case, the way we're looking at it clockwise. Notice that this is off center. As this guy rotates, the vanes are actually on springs. They travel in and out to maintain a seal around this outside edge. And since it is offset, as they rotate, the area, the volume here gets larger, which creates a suction, pulls the hydraulic fluid into the pump. And on the other side, as they get the area gets smaller, it forces it out the outlet. Hydraulic pump ratings are assigned by the pump manufacturer and are the main factors in determining pump use. Most common pump ratings include the following: displacement, gallons per minute, flow rate, pressure, and volumetric efficiency. Displacement is volume of hydraulic fluid moved during each revolution of the pump shaft. Displacement per minute represents the amount of fluid a pump displaces in 1 minute. So, displacement cubic inches per minute is equal to revolutions per minute times the displacement. Gallon per minute In this case, pump displaces 4 cubic inches per revolution. Motor shaft is run at 1725 RPM. Okay, so here's a question. Those of you that have had me, or Landon, or anybody else for that matter, those of you that had basic electricity and or motors and controls, how many pole motor is that? It's running 1720 RPM. Somebody, anybody?
That'd be a 2-pole motor.
That's a really good guess and it's dead wrong.
Was a guess,
Yeah.
so I'll take it.
Anybody remember what formula it is?
No.
That look familiar to anybody?
I didn't take that class, the one that involves motor control.
That's like the one time you didn't raise your hand in this class too. It's actually 60 times 2 times frequency, but 60 times 2 is always 120.
I don't think you ever showed us that.
Okay. So if, what is the frequency in North America?
60.
60 hertz. So 120 times 60?
7,200.
So how many poles do you have to have in order to get 1,800 RPM output?
6. Yeah, 6.
For 1,800 RPM output?
Oh wait, I'm doing 1,200, my bad. Sorry.
4.
I was close.
Divide 7,200 by 4, you get 1,800. That's synchronous speed of the RMS rotating magnetic field. And then you have to have some slip or you don't have any torque. So the actual output of the motor is 1725. If it was a 2-pole motor, you get a 3,600 RPM motor. And when you take into account the slip, it's actually 3,450-ish. So, need a little bit of trivia there for you. And you thought that the stuff you learned in those classes was only for those classes. Pressure rating is the highest amount of pressure at which a pump can continually create flow without premature wear. Pump must be specified with a higher pressure rating than the fluid power's system maximum pressure requirement. Why do you reckon that might be?
In case of a spike of pressure, so it's like it's able to.
That's a small part of it.
Oh.
Matthew?
If there's no pressure relief out in the circuit, wherever the weakest point is, the circuit is where it's going, the pipe is going to burst and everything will.
Okay, but that doesn't have anything to do with why you want a higher pressure rating on the pump than what maximum system pressure is going to be. I mean, you're right, but that doesn't answer this question.
So basically what you'd want to do is you'd want to have a high enough pressure rating to handle all of the pressure requirement of the system as well as any overpressure in the system if there is any.
Okay, but why?
I think it would help prevent the pipes busting or anything like that.
That's why you put pressure relief in the system.
Does it protect the equipment?
Protects the pump. You have a pump that is capable of producing higher pressure than you need, then you're not running the pump at its maximum all the time. But that will greatly reduce the life of the pump. You know, if you get one that, say you need 5,000 PSI and you have one that's capable of 7,500, you're gonna be running at roughly 2/3 of what its maximum is. It'll do that all day long, every day for years. You need 5,000 pounds, or not 5,000, yeah, 5,000 pounds pressure, and you get a pump that's capable of 5,000 pounds pressure, you're running it balls to the wall all the time, and you'll wear it out in just a little bit of no time. Okay. Volumetric efficiency is what the pump is capable of versus what the actual flow-through system is going to be. Every time you turn a corner, pass through a device, whatever, you have a little bit of pressure drop. You'll also typically see a reduction in flow. Positive displacement pump is a pump that has a positive seal between its inlet and its outlet and moves a specific volume of hydraulic oil with each revolution of the shaft. They're the only type of pump that are used in hydraulic systems and equipment. Positive displacement pumps are typically categorized as fixed or variable. So positive displacement means that if you pick up 3 cubic inches of oil at the inlet, you're going to get 3 cubic inches of oil out the outlet. Fixed displacement. Notice that the triangle is filled in. It's hydraulic. Also only going one direction. So it's a unidirectional pump. Variable displacement has the arrow through it. But do either of those schematic symbols tell you what kind of pump it is?
Is it a hydraulic pump?
Well, yeah, but is it a gear pump? Is it a piston pump? Is it a vane pump? Yeah, that hydraulic symbol does not tell you what kind of pump it is. Hydraulic pump types. Gear, vane, and piston, like I just said. All hydraulic pumps create fluid flow by following 4 basic steps with some differences according to the pump type. Gear pump, that's what I was talking about. You would think that the fluid would want to go like that. Well, there's no way to capture the oil in here. It only gets captured here because these lobes are in contact with the inner surface of the pump housing. And you guys ever watch your mom make a cake or something whenever you were little? She'd use the electric mixer. Feed her spin this direction and all the shit goes out the front of it. That's exactly the opposite here. That's a lobe pump. Works very, very similar to the gear pump, only there is a positive seal here. Where on the gear pump there's not. You also notice that it specifies that the shaft is keyed. That makes sure that lobe, or the impeller is always in that orientation with the shaft. So if this one is keyed, that one is not. What keeps that one in sync?
The first lobe.
The bottom lobe. Okay. Internal gear.
That's cool.
That's pretty wonky, isn't it? Anything about those is both sets of gears, the internal and the external, both move. You know, they're being driven here, so as this goes around, so does this. So you're actually pumping twice the amount in the same physical space as you would with a standard gear pump.
The inner gear is driven.
Yes,
The crescent piece, it doesn't move. And
it
the
does
gears-
not.
Sweet.
It just provides a seal for there and there. That's all it does. And then that's a gear rotor. Vane pump, we already looked at that. I was going to reach up here and try to do that, but I can't. But I have already tried. Yeah, as the rotor spins, the vanes expand and contract. They're spring loaded. So it keeps them in contact with the, and then of course, once you get the spinning, there is centrifugal force there too. Piston pump is a hydraulic pump in which fluid flow is produced by reciprocating pistons. Types of piston pumps include inline axial, bent axial, variable axis, variable bent axis, radial, and variable radial. All kind of different options you can have on there. Variable displacement control methods, load sensing, torque, horsepower limiter, and electronic displacement. Load sensing pump can tell based on the pressure in the system if it needs to produce more flow or not. So is the pump smart? Matthew?
As far as it's built to be, depends on how it's built.
It's a hunk of steel. What creates pressure?
Resistance, right?
Hmm?
Resistance.
Resistance to flow. If you have, say, the Hoover Dam out in Arizona, Colorado, the Hoover Dam is the border between the two. Is that right? That's one place I've always wanted to go. Never had gotten to go out there. You think there's pressure on the dam wall? I'm looking at you.
Yes, it would be,
Okay, so
because of resistance.
why is there pressure on the wall of that dam?
Because exerted force against resistance creates pressure.
The wall is resisting letting the water go down the river.
Correct.
So pressure is caused by a resistance to flow. Okay, so my load sensing pump, if I have no movement in my system at all, going to have one pressure, right? Whatever my pressure relief is set at. But if I have things moving, I'm still resisting the flow of the fluid, but I'm allowing some of it to move. My pressure goes down. That's how the pump knows, based on the load that it sees, hey, I'm supposed to be running at this pressure and something is moving, there's fluid escaping from where I'm supposed to be applying pressure to, so I need to increase the pressure to compensate for it. Okay, that makes sense?
Correct. So it's compensating pressure.
Several other people looking at me like, huh?
What it's doing is it's compensating pressure that the pressure drop when something's moving. It's compensating that pressure loss. So it raises it up. That's pressure compensation.
When you allow the cylinder to move, you're actually increasing the volume in the system. And so in order to maintain the same pressure, you have to boost it up, give it more flow. Torque and horsepower limiter or electronic displacement. The electronic displacement, I've never personally seen one of those. Yeah, electronic displacement, there's electronic pressure sensors in the system that say, hey, this is what system pressure is, and you need to adjust yourself based on what the feedback from the system, the sensors in the system are telling you. There's pressure compensated. That's your main shaft. What's known as a wobble plate. And it changes its pitch based on what this feedback signal is doing. Provides fluid here. Of course, it's spring return, but it pushes, bringing it more vertical. The less angle it has, the less these pistons move. The more angle it has, the more they move. So they displace a lot more fluid when the plate is tilted than when it is straight up and down. Okay, Matthew?
So as the plate is moving, it's compensating the pressure for the load that causes the pressure to drop.
Yeah, that's what's known as a pressure compensated pump.
Yes.
Okay, Cindy?
Should be.
Torque or horsepower limit. Torque or horsepower limiter control varies the displacement to maintain a constant horsepower or torque input when the speed of the prime mover does not change. Concept of this type of control is when higher flow is required, pressure drops to supply the needed flow. So we're intentionally allowing pressure to drop when we need more flow. You can also compensate for some pressure and or flow loss with an accumulator. That's electronic displacement. It just uses electronic signals to vary the wobble on the plate. Double and triple pumps. Okay, pump operation safety. Potential safety issues are present during troubleshooting, removal and repair, installation, and operation of hydraulic pumps. Failure to adhere to proper safety practices can result in injury and or death to those working on or near the hydraulic pump, as well as irreparable equipment damage. So it can kill you. Pump removal, repair safety, and verify that the fluid temperature is below 120 degrees F. Anything above that will burn guaranteed to burn you. Verify that the system pressure is at 0. Lockout tag out the pump to prevent inadvertent starting. Capture any fluid spillage. Otherwise, people step in it, slip, fall. Avoid pinch points. You actually smash your finger up if you try hard enough. And test the pump to verify proper operation. That would be after you've repaired it. 3 safety issues to consider when installing the pump's weight. You never want to put yourself beneath or below any load. It's elevated, no matter how heavy or how light it is. You want to make sure you have proper alignment with the pump, the prime mover. There is typically some sort of coupling in there that takes up some misalignment. And then proper hose connections. You want to make sure that you have the outlet of the pump connected to the pressure side of your system. Instead of the return, you're dumping shit straight back in the tank. Pump handling and lifting equipment. Fork truck. Gantry crane. Chain hoist, come along. Or overhead. That's if they're too heavy to lift. Of course, unless you're Bruticus, most of them are going to be too heavy to lift. Pump prime mover alignment. Pump shaft must be aligned with the shaft on the prime mover and should be checked with dial indicator. Or they do have laser alignment tools. We actually have a couple of them out here. Mounting pad or adapter must be concentric with the pump shaft to prevent bearing failure. Concentricity is particularly important if the shaft is connected with a rigid coupling as opposed to a flexible coupling. I would never put a rigid coupling on a system no matter what. They do have flexible couplings that are capable of some really high torques, and they allow for minor misalignments. Proper hose connections. Output section of the pump is typically the highest point of pressure in the hydraulic circuit because it hasn't passed through any devices or anything to have pressure drop. Connection to the output of the pump needs to be performed properly, or the hose could burst at the point of connection and cause damage to both persons and property. So double check, make sure everything's tight. Prevent hazards from ruptured hoses. It must be verified that the pump and attached hoses are in good working order. And assuming that the last person that replaced the hose whenever it failed put the right hose on it. And while it was running, it was been running like that for years, I would still check every single hose. Make sure that one is not dry rotting or other failures. And also make sure that every hose on it has pressure rating on it. And make sure that it's at least 150% of what the pump is capable of. Maybe not what the pump is running at, but what it's capable of. So hoses are almost never